Course 3, Investigation 10, we are looking at simple interest and compound interest, and also looking at the rule of 72 with compound interest. So with this, let's just start out thinking about simple interest and when you deposit money in a bank. So this says when you deposit money, bank doesn't just simply hold on to that money for safekeeping. Instead, it invests it in other places to potentially make a profit. So the bank does this, and to kind of thank you for allowing them to use your money, you get a little bit of money back. So when this happens, the amount that you actually deposit is considered the principal amount, and the amount of the money that the bank pays you is called interest. And typically this is a percentage of how much you put in. So a percent of that principal. So we have two different types of interest that could happen: simple interest and compound interest. Simple interest doesn't actually happen all that often. It's a very basic idea, but most people end up getting compound interest for those deposits that they make. So simple interest is paid on the principal only and not paid on any of the accumulated interest. For instance, if we had $100 in the account, so if for year one I deposited $100, then if I find 6% of that, I would say that I'm getting $6 for that year. So we would add it, and the next year I would have $106. Well, that next year we're not actually getting that interest on $106, we're still having it on $100, so I add only $6. And then it happens again. The next year we only get $6, and so we have a total of $118 by the end of the third year. So put a different way, we see it like this. If we put in $100, in the first year interest we have $6, second year, third year, also $6 for a total of $118. But once again, this doesn't happen very often. Most of the time we actually have compound interest. In compound interest, the interest is paid on the accumulated interest as well as on the principal. So if we deposit $100, that first year will still only give us $6, but after that, I won't be having interest on just the $100. I'll have interest on the $106, and then on and on and on. So, for instance, this is what it would look like. First year, we would have $100 plus 6. So by the beginning of that second year, we would have $106. But at that point, then it's going to take $106 and find 6% of that, which ends up being $6.36, a little bit more than that $6 from the first year. And so we add it on top. So by the beginning of that third year, I have $112.36. After that, I take my $112.36 and find 6% of that, which is $6.74. Notice that we're growing slowly, but we do get a little bit more each year, so that by the end of that third year, I have $119. Well, this may seem like, oh, who cares? It's $1.10 difference between the 3 years. It makes a big difference by the end of something like 50 years. For example, if I were to just have simple interest adding that $6 each year, I would only have $400 after 50 years. If, though, I had compound interest for 50 years, I would have $1,842. I don't know about you, but I would much rather have compound interest on that $100 rather than just simple interest. There's over $1,400 difference between the two. So compound interest really does make a difference, and especially when you're depositing money, it's a very good thing to have. So let's try it out on this investment. So this says over the last century, the stock market's average annual rate of return has been about 10%. Make a table that shows the value of a $1,000 investment growing 10% each year after 1, 2, 3, 4 years. Okay, so let's do that. We should say number of years for my first column, and then the money that we're going to receive. Alrighty, so if I do this, what I'm going to do is I started with $1,000 and I want 10% of that. Well, that gives me $100 that I add on. So after that first year, I have $1,100. And this is compound interest, so I'm going to now take that $1,100 and multiply it by 10%. Well, when I get that, that's $110. So I add that on top, and now, after 2 years, I have $1,210. I keep doing this, 12, 10 times 0.1, and I get $121. So I add that on top, and I get $1,331. Okay, and you can see where this is going. I'm going to take that 1,331, multiply it by 10%, add that on top, and so on and so forth. By the fourth year, I get $1,464.10, and by the fifth year, I am already at $1,610.51 using that compound interest. So we can see how quickly it can start growing after a few years using compound interest. This is why people like to put their money in the stock market to potentially get that growth. Doesn't always happen because stock market is always some amount of risk, but it is a good potential growth. What we are actually doing here with compound interest is really a geometric sequence. And we can show this geometric sequence using a recursive formula like we've seen before, showing a sub 1, so the first number in the sequence is 1,000, and then we show what happens to each one afterwards. Well, what I'm really doing is if I am taking 10% increase, well, that's like having 110% of the original, like we've learned before, which we can put in its decimal form as 1.1. That's actually what I'm multiplying to each one of these numbers as I go along. For example, if I went back up here and took that $1,331, and instead of multiplying it by 0.1 and adding it on, I could get straight to my next number by just multiplying by 1.1. That would be fine as well. So we show that in our recursive formula by putting a sub n, so the next number in the sequence, equals 1.1 times the previous term in the sequence, a sub n minus 1. So let's answer a few different questions here, and what we need now is a calculator, because most compound growth is actually shown by using a calculator. It gets very tough with all of those decimals very quickly, so we use our resources. So most calculators can calculate compound interest, and so we could do this that is shown, 1,000 times 1.15 times. So when we do that, we get to a number that matches exactly what we had above at the last time in our table, because what this is showing is just year 1, year 2, year 3, year 4, and year 5. So it should give us the same number as up here, which is $1,610.51. Now, so do they match? Yes, they do. Notice that 1.1 occurs repeatedly. So instead of just multiplying it 5 times in a row, we should use exponents. And what we should really plug in our calculator is this right here. So what do all of those pieces mean? Because we can actually replicate this with different numbers and different percent interests. So the formula that we are actually using is right here. V is the current value, okay? So in this case, V would end up being, after those 5 years, $1,610.51. P is the principal, so in this case, $1,000, what we put in at the beginning. I is the interest, in this case 10%, but we're going to show it as 0.1. Okay, and then you'll notice in the formula that we're adding on 1. That represents that 100% that we begin with, that we're adding that 10% to each time. And n, our exponent, is how many periods we are going through with that interest. In this case, we're talking about years, so we have 5 years worth of interest. Okay, and that interest compounds each year. So we would actually plug this into our calculator by saying, and most of these numbers are pretty normal, 1,000 times 1.1, and then we use a little caret when we're in a calculator. So caret to the 5th power. Carets show what is our exponent. And so we would plug that in and we would end up with this $1,610.51. So continuing on with this calculator, let's use a new situation here. So although the average rate of return for stock market has been about 10%, it rises more some years and falls in others. Thus, stocks are usually considered a long-term investment. So if a 25-year-old invested $1,000 in a mutual fund that averaged 10% return each year, what would the value be when the person is 65 years old? Well, we start with what we had up here and we say our current value equals our principal, which in this case is still 1,000, times the 1 plus our interest, which is 0.1. And then how many years? Well, from 25 to 65, that's 40 years. So we would plug into our calculator 1,000 times 1.1 to the 40th power. When we do that, we get a pretty big number, and I'll just do it on my calculator really quick. As I do this, you should be following along with your calculator as well, of course. But when we plug that in, we get a number that is $45,259, and rounded to the nearest penny, 26 cents. So quite a bit of money after those 40 years just by putting in $1,000. It has multiplied by 45 times. That's pretty huge. If we were to round this to the nearest $1,000, we would be about at $45,000. Let's try another one with this compound interest using our calculators. So Ben Franklin thought the funds he left to Boston and Philadelphia would earn 5% interest annually. Find the value of a $4,500 investment earning 5% interest after 100 years. Well, we plug that all into our formula and say our principal amount, our beginning amount, is $4,500. And then we're going to multiply that by 1 plus my percent as a decimal, so 0.05. And then our exponent here is going to be how many years, and in this case 100 years. So what we're putting into our calculator is 4,500 times 1.05 to the 100th power. Well, go ahead and do that. Take a second to do that, and go ahead and round it to the nearest $1,000. So 4,500 times 1.05 to the 100th power gives us exactly, I'll show you the exact amount, $591,755.66. So we would say, rounded to the nearest thousand, $592,000. That's pretty impressive. Okay, and then number 5. Find the difference after 30 years of a $5,000 investment that earns 6% versus one that earns 5%. So let's start with that 6%. And we would say that we are doing $5,000 times 1 plus 0.06, so 1.06 to 30 years. We'll plug that in a second. And then our 5% one is going to say something very similar, so 5,000 times 1.05 to the 30th power. When we do this, what we end up getting is, and you can take a second, pause the video, plug it into your calculator, $28,717.46 versus $21,609.71. That is a difference, so subtract these two, a difference of about $7,107.75. It's with the same number of years, just one tiny little percent makes a $7,000 difference. That's something significant, that's for sure. Okay, now moving along, we use this rule of 72 as a rule of thumb to figure out how quickly something might double. How much time is it going to take for my $1,000 investment to turn into $2,000? Well, what the rule of 72 says is that if I take 72 divided by my growth rate or my interest rate, gives me how many years it will take. Okay, so if I have compound interest that goes annually, I'll figure out how much time in years. If that interest happens every month, I'll figure out how many months. This is a pretty good rule of thumb. It's not exact though. It's not going to be exact and tell you how many years to the day of how much time it will take to double your money. It's a good estimate though. So for example, and you can go to this YouTube if you would like a little bit more explanation and examples of the rule of 72, but let's use it in context here. So if I have something like 6%, what I would do to figure out how much time it takes for my investment to double is take 72 divided by my growth rate, in this case 6%. That gives me 12. And if we are talking about years, which I am assuming we are saying it will take 12 years for that investment to double how much I had before. So if I started with $1,000 right here at 0 years, by 12 years at that 6% growth, I would have $2,000. By another 12 years, it will double from there, so $4,000, and it will double again by the time we get to 36 years. So every 12 years, I take that amount and double it. Okay, and we'll practice a couple more of those in just a moment, but the last little bit of new information for this investigation is about exponential growth. Compound interest is exponential growth. That actually comes from the formula where we say V equals my principal amount plus my interest rate time to the number of years. Because I have a variable in that exponent right there, this is an exponential growth equation, okay, or an exponential function just in general. I know it's growing because I am going higher than 1 in this growth. I am adding 5% each year. If I was decreasing 5% each year, and it would say something like this, I'm getting a little ahead of myself, you'll get into a lesson of this later, but if I were decreasing 5%, so I only had 95% left each year, then we would be talking about exponential decay. Whole other topic, but it's always good to start thinking about some of those ideas. But in general, exponential growth starts out pretty slow. You can see with this curve right here, it starts out slower than even just linear growth, but it starts to surpass linear growth pretty quickly. Okay, so after that, it just continues to grow and grow and grow and grow, whereas linear growth continues steady. Okay, so we definitely, especially when we're talking about money and interest and putting in money to save for later, we would much rather have exponential growth rather than linear growth. So let's answer a few questions to finish this investigation. So considering example number 2, which we just did a second ago, predict the value of a $1,000 investment growing at 12% for 36 years. So instead of taking this 6% that I had, I want to know what it would be like if I had 12%. Well, we can estimate that if you would like. Take a second to estimate it, get a general idea. We could also put it into an equation to say my value is going to be $1,000 times 1.12, that's my 12%, to the 36th power. When we do that, and I'll just plug that in just so you can see if your estimate was close or not. So 1,000 times 1.12 to the 36th power gives us $59,000, 135.57 cents. So hopefully your prediction was pretty close to that, but that's the exact money amount. Okay, so number 7, let's see if we were to apply the rule of 72 to this, how long would it take for me to double that 1,000 to become 2,000? Well, if I use the rule of 72, I'm going to use 72 divided by my growth rate, which is 12%, giving me 6 years. So it's going to double every 6 years. Well, let me just make a little table over here. If I double every 6 years, so here's my years, here's my money. At 0 years, I'm going to be at that $1,000. But by 6 years, I'm going to be at 2,000. By 12 years, I'm going to be at 4,000. 18, I'm going to be at 8,000. Oops. by 24 years, I'm going to be at $16,000. And by 30, we're almost there. We're going to be at, let's see, where was I? $32,000. And here's my 36 years. I'm going to be at $64,000. So by using the rule of 72, we would estimate that our money would be at about $64,000. Looking between our exact amount and our estimated amount, for an estimation, that's not too bad. That's pretty close. Yes, we're off by a little bit, but it's truly just an approximation using the rule of 72. Okay, so comparing this at 12% to my earlier amount, so we have $64,000 after 36 years, compared to at 36 years, we only have $8,000 at that 6%. Makes a big difference between these two. By doubling the interest rate, I have basically multiplied my amount of money by 8 by the end of that time. Pretty incredible difference. Okay, a couple more here. A property owner was going away on business for 3 weeks and wanted to hire a person to care for the property. 2 people applied. The first person wanted to be paid $100 per day. The second wanted a penny for the first day, 2 cents for the second, 4 for the third, and so on and so forth, doubling every day for 3 weeks. Which person should we pay, or which person should the property owner hire? Well, let's put it into perspective. For the first person, they want, for the 21 days, they want $100 per day. So they would get $2,100 by the end of it. The second person starts out, and we'll just go ahead and make a formula for this. We'll say that our value starts with 1 penny, so 0.01, and it doubles every day. So we would put a 2 right here. It's like 100% increase. So we double every day for 3 weeks. That's 21 days. Well, let's plug that into our calculator and see which one we should hire. So 0.01 times 2 to the 21st power. And by the end of those 3 weeks, the property owner would have to pay $20,971.52. This is the power of compound interest. This is how weak linear growth can be compared to exponential growth. Same amount of days, just a very different method of going about choosing. So I'll leave it up to you. Which would you hire? Which would you rather do? Hopefully the choice is extremely clear. And 10 and 11. So as a steady growth rate of 1.2%, about how long would it take for the world's population to double? This is where we use our approximation with 72, and we put our growth rate, so 1.2. Ends up that it would take 60 years for the population to double. And then our last one. If the country energy needs increase 3% per year, then its energy needs will double in about how many years? So 72 divided by my 3% will be at about 24 years. All right. Well, that is the end of the investigation. I hope you have a clearer understanding between simple interest and compound interest, and how powerful compound interest can truly be, especially when you have many years to build up your money. All right, I hope this helps with your homework and for studying.